The study of curved surfaces in differential geometry is certainly daunting. But most of the subject's complexity doesn't actually stem from the curved surfaces themselves, but rather from the curvilinear coordinate systems we must use to describe those surfaces. Indeed, what does it mean for coordinate systems to be arbitrary or curvilinear in the first place? And how can we gain a better understanding of them intuitively? Today, our path towards deciphering the precise physical meaning of the equations of general relativity continues. This is Dialect, with an introduction to curvilinear coordinates. Let's begin with an ordinary Cartesian coordinate system on a flat surface. In the most basic sense, each line in this system represents some constant value, typically a distance out from the origin along one of the coordinate axes. But next, let's draw another coordinate system upon it, a curvilinear one. Obviously, this system is curvilinear because its lines aren't straight. But what precisely are we trying to indicate with these curved lines in the first place? Well, essentially, just like with the Cartesian grid, we're trying to say that each line of this curvilinear system represents some constant value. But obviously, it's not the same value which belongs to our Euclidean system. Indeed, we can think of such a value as belonging to some other system or frame of reference, one which is being mapped into our Cartesian space. Meaning, if we examine a single grid of the curvilinear system, we can recognize that in this other space or frame of reference, this length here actually spans the same distance as this length here, despite them having different lengths in our Cartesian space. This other space where the curvilinear coordinates live is called a parametric space, whose variables will designate with the lowercase letters u and v. Now, just like our Cartesian grid, the parametric space is perfectly flat and Euclidean, because of course in this space there's nothing for the coordinates to be curved relative to. Let's now task ourselves with precisely describing these curvilinear coordinates from within our Euclidean system. To do this, we will represent every point along a coordinate curve as a vector that reaches from the origin of our Euclidean system to that point. Let's designate this vector with the uppercase letter v. Next, we recognize that the x and y components of this vector can then be expressed as multivariable functions of the parametric space. For instance, if the curvilinear coordinates we were using were, say, polar coordinates, then any point on our Euclidean space could then be expressed via the vector v equals r cosine theta, r sine theta. But keeping our curvilinear system arbitrary for the moment, let's say we want to determine the distance that a change of 1 unit in the parametric space spans back in our Cartesian space. Well, to do that, we can draw two vectors, one which reaches to the start point of the curvilinear unit, and one which reaches to its end point. Then, to find the approximate distance and direction that this curvilinear unit spans in the Euclidean system, we simply take the difference between these two vectors. Doing this everywhere allows us to envision these curvilinear coordinates as a sort of flow field across our Euclidean space. Areas where the vectors are larger in magnitude represent areas where the curvilinear coordinates are changing more rapidly, whereas areas with smaller vectors represent less rapid changes. We can thus represent our curvilinear coordinates as vector fields on our Euclidean surface. Now, back in our parametric space, let's imagine taking two hotwheels and setting them into motion such that, within this parametric space, they traverse equal unit distances in equal unit times. Then, in the Cartesian space, what these vectors will describe is the approximate velocity of these hotwheels as they move along the coordinate curves. But we can make this more precise. Instead of considering the distance spanned by one curvilinear unit, let's now consider the distance spanned by half a curvilinear unit. Again, we draw two vectors spanning the start and end point of the half unit and take their difference. Now, however, let's divide the magnitude of this vector by 1/2 in order to get the amount of Euclidean distance spanned per change in curvilinear unit. Repeating this process to its infinitesimal limit yields a vector tangent to the coordinate curve whose magnitude represents the coordinate velocity of the curve at that point. That is, the precise velocity our Hot Wheels would have traveling through that point. Do this for the other coordinate direction as well, and then about any point we have two vectors describing the respective velocities of Hot Wheels traveling in those directions through that point. But what do these velocity vectors represent back in the parametric space? Well, obviously, they represent the constant velocity of the Hot Wheels which are traversing unit distances in unit times. But there's another connection we can make, which is that they represent the basis vectors of the parametric space. That is, back in the Cartesian system, these tangent vectors characterize a tangent line whose coordinate intervals represent what the respective parametric axis looks like about any infinitesimal region. Indeed, draw out the tangent axes in both coordinate directions about a point, and you'll get a linear coordinate system depicting how the parametric space there infinitesimally compares to the Euclidean space. Now, as we move along the coordinate curves, this infinitesimal coordinate system will change. It may skew, stretch, or shrink along with the basis vectors, but because of its infinitesimal nature, it always remains linear, which makes it easy to work with. For instance, if we consider a small Euclidean distance element dx squared plus dy squared about a given point, we can now describe this element in terms of the parametric basis. We simply note that this distance element is, via the law of cosines, the dot product of the u basis vector with itself times du squared plus the dot product of the v basis vector with itself times dv squared plus twice the dot product of the u basis vector with the v basis vector times du dv. These dot product coefficients, when assembled together, yield an important tool called the metric tensor. But for now, we want to know more about the motion of our Hot Wheels. We've already determined their velocity as they move along the coordinate curves. But now, let's ask, can we also determine their acceleration? Well, that just simply requires taking the difference between the Hot Wheels velocity at two nearby points and then dividing by the amount of change in the curvilinear coordinate. If we do this in an infinitesimal manner in both coordinate directions about any point, we will get two acceleration vectors there, representing the acceleration of the Hot Wheels traveling along the respective coordinate curves at that point. Mathematically, these are the derivatives of the basis vectors when those basis vectors are transported along their respective basis directions. Unfortunately, these two vectors don't completely characterize the acceleration of the coordinate system about that point. This is because we also need to consider how the velocity differs for two nearby Hot Wheels traveling in the same coordinate direction. That is, we want to know how the u basis vector changes as we transport it in the v direction, and also how the v basis vector changes as we transport it in the u direction. Another way to think of it is, if we picture the coordinate flow along the u direction, we want to know not only the gradient of this flow along the u direction, but also along the v direction. And similarly, for the coordinate flow in the v direction, we want to know the gradient of the flow not only in the v direction, but also in the u direction. Now, for the sake of coordinate continuity, these two cross gradients must have the same value. That is, the rate of change in our u basis vector when transported along the v direction must equal the rate of change in our v basis vector when transported in the u direction. This is known as the Levi-Civita condition, and what it ensures is that our coordinate lines are always well behaved and never fail to close. So for instance here, since the u basis vector rotates down and shrinks as it moves in the v direction, the v basis vector has to rotate in and also shrink to compensate for this. If we think of it in terms of coordinate flow, we can recognize that our v basis vector is like a piece of driftwood on the u-coordinate river. Since the flow of the u river is faster down here than up here, our driftwood is thus subject to a rotation or curl as it follows the flow. Moreover, if we imagine our driftwood as being somewhat elastic, such that it also grows or shrinks wherever the river diverges or converges, then it will also shrink as it follows the u flow, in accordance with the convergence of the river there. A similar analysis with the u basis vector on the v-coordinate river reveals an interesting implication of the Levi-Civita condition, which is that the divergence or convergence of one coordinate flow must, in a sense, always be compensated by a curl in the other coordinate flow. Alright, so to characterize the acceleration of our curvilinear coordinate system across the Euclidean surface, we merely need to transport our two basis vectors along each coordinate direction, and then take the change or derivative of these transported vectors with respect to the direction along which they were transported. This yields 4 total acceleration vectors, 2 of which are identical. Next, if we then expand out our infinitesimal parametric space about our point of interest, we can then express these acceleration vectors in terms of the parametric basis. This yields 8 total vectors, though only 6 independent ones. The corresponding magnitudes of these vectors in the parametric space are known as the Christoffel symbols. The value of this Christoffel symbol, for instance, is -3/5, since it spans 3/5 the length of the u basis vector and is oriented in the opposite direction. Alright, let's now summarize our complete characterization of a curvilinear system. First, we establish a position vector v which reaches to any point on the coordinate curves. Then, by taking the partial derivatives of this vector with respect to the parametric variables u and v about that point, we get how the basis vectors of the parametric space look when transformed into our Euclidean space there. Second, by permuting the dot products of these transformed basis vectors at that point, we get the coefficients necessary for expressing Euclidean distances in terms of the parametric space there, i.e., the components of the metric tensor. Third, by taking all the respective partial derivatives of our two basis vectors, we get 4 vectors expressing the acceleration of our curvilinear coordinate system about that point. Lastly, to turn these acceleration vectors into Christoffel symbols, we must decompose them into components of the parametric basis. Mathematically, we can do this by taking the dot product of each acceleration vector with each respective basis vector. But additionally, we must normalize all vectors involved by the length of the relevant basis vector, in order to ensure all our Euclidean space values are being converted back into parametric space values. This yields the formulas for our 8 Christoffel symbols. Next, let's do an example by taking our curvilinear coordinates to be polar coordinates. In this case, the vector v equals r cosine theta, r sine theta. Taking its partial derivatives with respect to r and theta gives us the two basis vectors, cosine theta, sine theta, and minus r sine theta, r cosine theta. These are the velocity vectors of our Hot Wheels at any point as they move along the different coordinate directions. Given, of course, they are traveling unit distances in unit times back in the parametric space. Next, permuting the dot products of the basis vectors yields the values 1, r squared, and 0. These are the components of the metric tensor, or the coefficients of the arc length formula. Lastly, taking partial derivatives of the basis vectors with respect to r and theta, and expressing their components in the polar basis, yields the 8 Christoffel symbols, the only non-zero ones of which turn out to be minus r and 1 over r. Now we can note that, for a Hot Wheel traveling along a curve of constant radius, minus r is the value of its centripetal acceleration. A Hot Wheel traveling along a line of constant theta, meanwhile, experiences no change in velocity. Next, we can note that the Christoffel value 1 over r is the value of the gradient relative to the polar basis of the theta coordinate flow as we move in the r direction, or the amount by which two Hot Wheels' tangential speeds will differ per a small change in radius. Similarly, it's also the gradient of the r-coordinate flow if we move in the theta direction, or the rate at which the tangential separation between two Hot Wheels is increasing if they are traveling lines of constant theta. Again, the Christoffel symbols are all expressed relative to the polar basis, which changes from point to point across our Euclidean space. Now, the reason the minus r Christoffel symbol has the same magnitude as its corresponding acceleration vector does in Euclidean space is because the radial basis vector does in fact not change, and has the same length everywhere as a Euclidean basis vector. The length of our theta basis vector, however, does change from point to point. And consequently, the theta component Christoffel symbols require a 1 over r conversion factor to convert from the Euclidean distances to the parametric distances. This should be fairly apparent, since 1 over r is the coefficient which, in our radian units, takes a distance along the circumference of a circle and converts it into that of an angle. Consider now our elastic driftwood theta basis vector upon the surface of the r-coordinate flow. We see that, as it moves with the r-coordinate flow, it experiences no rotation, but rather only grows in length. The r-coordinate flow for polar coordinates thus represents pure divergence. Meanwhile, our r-basis driftwood on the theta river experiences no stretching or shrinking, but rather is subject to a continuous rotation. The theta coordinate flow for polar coordinates thus represents pure curl. In accordance with the Levi-Civita condition, we can then recognize that the divergence of the r-coordinate flow is accounted for by the curl of the theta coordinate flow, or vice versa. Lastly, the Christoffel symbols can help us determine what paths in the parametric space will correspond to geodesics in the Euclidean space. To see how, let's say we have a Hot Wheel moving in the parametric space with a velocity that is described by one radial basis vector and one theta basis vector. If it were to maintain this coordinate velocity in the parametric space, then the total acceleration it would feel in the Euclidean space would be equal to the sum of the three Christoffel components there. To travel a geodesic or straight line path in the Euclidean space, then, this Hot Wheel needs to ensure its total Euclidean acceleration is equal to 0. Thus, within the parametric space, it needs to accelerate equally and oppositely to the sum of the polar Christoffel symbols at that point. Now, this process can be repeated for an arbitrary hot wheel velocity, simply by breaking that velocity into its basis components and then scaling the Christoffel symbols accordingly. Hopefully you are beginning to see how, starting with just a single position vector, we can, simply via the power of differential expressions, begin to unlock all the descriptive capacity of curvilinear coordinates. But so far we have only dealt with flat surfaces. What happens when we move to curved ones? The good news is that the procedure established here for flat surfaces generalizes quite easily to curved surfaces. That is, as we'll explore in upcoming videos, we can describe the curvilinear coordinates upon a curved surface, and thus describe that curved surface itself merely by drawing out a position vector from an origin and deriving various differential expressions from that vector. However, this procedure does have a drawback, because it requires us to refer to an external space in which the curved surface is embedded. Now, if we want to describe the curved surface without ever leaving it, well, that's when the real fun begins. Because the equations used here won't quite suffice anymore, and we'll need to rethink our strategy. But that's for future videos. For now, if you want to learn more about curvilinear coordinates and their relation to general relativity, consider checking out our metric tensor trilogy, or our video on conceptualizing the Christoffel symbols, both of which are linked in the description below. Otherwise, until later, stay tuned. This has been Dialect. Thanks for watching.